Hello and welcome to SPE's Symposium on Artificial Intelligence. It would have been lovely to be there in person with all of you, but unfortunately we cannot do that, so I'm pre-recording the presentation for you. Today I'm going to be addressing the necessity for collaboration between data scientists and domain experts in doing any kind of project related to data science, machine learning, or artificial intelligence in the oil and gas industry. My name is Patrick Bungert. I'm the Vice President for Artificial Intelligence at Samsung SDS, previously with Algorithmica Technologies, where I've spent about 15 years plus in the oil and gas industry doing projects around data science and artificial intelligence. So what I'm about to say stems really from my personal experience of running many projects around the world related to that subject matter in our industry. So let me begin by saying that any data science projects, and I'm going to use the phrase data science to also encompass machine learning and artificial intelligence, any kind of data science project begins, of course, with the data. We must, of course, discuss in connection with the data what we want to do, what is the problem that we want to solve, the question we want to answer, therefore what is the data that is likely to be helpful. And in that context, when we collect the data or extract the data from the process historian or the control system, we need to ask four major questions that data science always wants to know. The first is representativeness. Does the dataset reflect all of the different aspects of the domain? In other words, is every important variable covered in the dataset? In our industry, that's generally the case because we have process control systems and archive systems available that store all the data. If there were important variables that were not captured, then your control system most likely would not be in control of your operations, and that would be problematic. It is possible, however, that important information is not contained in the same software system. There are sometimes cases where the process control system deals with only the control relevant variables and the maintenance relevant variables are stored in a different database. So we must ask ourselves, do we have to collect data from a variety of systems here? The second is the dataset significant? Does it adequately reflect every important dynamic that we want to model? For instance, if you're looking to model very rare events, do these events occur sufficiently often in your data set to be modelable at all? If, for example, you're doing predictive maintenance, which is one of the most popular use cases, and you want to identify, diagnose a particular kind of event rather than simply saying this is an event, then you need to have multiple examples of that kind of event in your data. This is where some of the availability problems occur, because if expensive or large pieces of equipment fail, they fail so rarely that you might have one example, maybe two, in your data set, and that is not significant enough to do very much modeling. So we need to ask ourselves, is the data representative of the situation and is it significant for the problem that we want to solve? In some cases, the answers might be no. When we do then have the data that we do have access to, how much uncertainty is there in any value? And I'm not referring to just the sensor, but the entire path from the sensor via the analog to digital converter, via all the cabling and the control system and the various conversions that occur here until it ends up in the long-term databases of the archive system. There are multiple conversions taking place, and so we must ask, how uncertain is that value really? If I've measured a temperature to be 20.1 degrees, and then I measure the temperature to be 20.5 degrees, is that a different number, or is it also a different temperature? It may not be. So something to be aware of. Lastly, how accurate is it? How much deviation from reality is there? If I place a temperature measurement outside in a process plant that is occasionally in sunlight and occasionally drenched by rain, that has winter and summer temperature differences that are significant, that means the environment outside the plant significantly influences the temperature that the sensor picks up, which then may or may not be a reflection of the process conditions inside that plant. Or it may be. That needs to be looked at, which is why there is a question of how much deviation from reality really is there. So we ask multiple questions about the data that we have available, and who is going to answer these questions in a particular case. It is going to be domain experts, people who are at that plant, who work there, who are experienced, who know the various conditions, who've been there in the winter and the summer, who've been there during exceptional times when equipment has failed, who are there, of course, during the normal times so that they can distinguish. These are domain experts. The data scientists generally know very little about the plant, about the equipment, about the manner in which the data has been collected, or about what the data means exactly. And they require a tutorial, effectively, by the domain experts. Which leads me to my first big statement here: domain expertise is essential. Any data science project that I have seen or that I have been involved in where the domain expertise for one reason or another has been missing has failed. It has failed to lead to good results, and it has failed to be adopted by the group of end users. Sometimes this domain expertise is missing because the data scientists say, I don't want to know anything specific, just give me the data, I'll make the analysis for you. Projects like this will not succeed, certainly not in the oil and gas industry. Sometimes it has happened because the oil and gas company's management has said, okay, just get the data scientists to look at this. My domain experts, I don't want them involved, or they don't have time, things like this. Again, the project will fail. It needs to be a collaboration. So that works out a little bit like this elephant example that you may have heard of before. It's a popular story of a long time ago. The analog is 6 people, all of whom are blind, are being taken to an elephant and asked to touch the elephant. They have never seen an elephant before or experienced an elephant before. They touch it in various places and are supposed to say what it is. So if you touch only the trunk, then it seems thin and long, and then you might say it's a snake. If you touch these huge ears, you might think it's a fan. If you just touch the body, it feels like a wall. So these people are not wrong in what they say. They are right for the aspect that they see. They just don't see the entirety of the situation, and therefore they make these misjudgments. It's quite similar if, as a data scientist, you look at oil and gas data and you're lacking the context of the situation. You're looking at specific numbers or a specific time series, which is one of thousands, and you're lacking the understanding of why things happen the way they do. There are blips in the line, which any domain expert will be immediately able to explain to you. But if you don't obtain that explanation, listen to it and understand it, then it will just be a blip to you. So it is important to acquire a little domain knowledge. And that has to come from the people who already have that. Now, in practice, of course, with real human beings, we take time to learn what we know. So both the domain expert as well as the data scientist have spent substantial amounts of time, years of their lives, in university education or professional development. They've spent years of their lives gaining experience in their fields. And so this is something that you can't represent in the same person, right? You cannot take an educated, experienced data scientist and make him into a domain expert in a few weeks. And you cannot take a domain expert who has spent years in the oil and gas industry being experienced and make that person into a data scientist in a few weeks. That's just not realistic. So based on the mere fact that it takes many, many years to both educate and make the person be experienced means a very important conclusion. These two roles that we're talking about, the domain expert and the data scientist, they cannot be the same person. You need to have at least two people, and I'm going to get into later why you need more than that. The domain expert, apart from representing the investment of education and experience, needs to, of course, know certain practicalities. They will be able to apply the data science tools to the real workplace. They will know what data is available. They will be able to check the data for quality. And they, because they speak the lingo, will be able to communicate with the oil and gas stakeholders in the company and at the plant. On the other hand, the data scientist knows about the availability of tools to analyze data. They will be able to use those tools, configure those tools. They will be able to assess whether the model that's being developed is of good quality or not. And they will be able to communicate with the technical staff that are involved in the data science project, which could be software programmers, could be mathematicians, data analysts, database engineers, whoever is needed. So they do very different things and they have a different background, which is why I'm saying they cannot be the same person. Now that we've established that we need these two roles in the project, they of course need to collaborate with each other. The data scientists need some domain knowledge and the domain experts need some data science. So how I see this cooperation working is that it begins with the domain expert who defines the task. So the problem has to be stated in some scientifically exact manner. We want to solve this problem. Then the data scientist has to think what tools, software tools most likely, are going to be needed to solve that task. The domain expert then selects the data that is going to be representative and significant and relatively accurate about the situation that we're trying to display. The data scientist processes that data. There's usually a pre-processing step where data is being cleaned up, outliers are removed, things like that. And builds, using that data, some kind of tool, usually a mathematical model, an artificial intelligence model of some kind. The domain expert is then able to utilize that tool to extract a practical conclusion that that person can then implement. Now, before we go into implementation, of course, the models need to be tested, which is why these two experts now talk to each other about, does the model accurately reflect the situation? Are the conclusions that the model presents actionable? So the domain expert is likely to spot underfitting, which is where the model is not sufficiently accurate given the experimental data to really be useful. The domain expert is needed generally to do this unless the results are completely horrible, because it's only the domain expert who realizes just how accurate in very specific situations the model needs to be in order to be actionable. I say this from experience. I've seen many cases in practice, in real life, where all of the data science metrics about measuring accuracy, whether we're talking about accuracy, the F1 score, the area under the curve, or any of these usual measurements, look great. But the model is expected to work in a specific operational context that needs to be actionable in a human construct of an organization. And sometimes the accuracy is not good enough for that application, even though theoretically it looks great. I've seen the reverse as well, where theoretically the area under the curve or the F1 score looked very shaky, but applied to the specific situation, the model worked just fine. So the domain expert is really the person who can assess whether or not the model is applicable and accurate enough for the utilization in real life. On the other hand, it's the data scientist who spots overfitting, which is where the model is extremely accurate, but because it memorized the empirical data and it doesn't generalize beyond what it has seen. The domain expert generally doesn't see that because the model is just very accurate. So again, the two major problems of artificial intelligence, underfitting and overfitting, need 2 points of view to look at them. The data scientist is able to do something called feature engineering, which allows the data scientist to spot the crucial data that is needed in order to make the model work. Feature engineering generally consists of a couple of steps. First of all, we generate some more features, which may need domain expertise input. And then secondly, we select from that list the features that are going to be instrumental. And that selection generally results in ignoring a large number of features and honing in on a few that are particularly expressive. The domain expert, on the other hand, is going to act on the conclusions. He's the person who is able to do something with the results of the software. Lastly, I'm going to talk about bias. This is not cultural bias or not data bias. It is assumption bias. The domain expert is biased in the sense that the domain expert holds certain assumptions about how reality works in this particular context, and the data scientist does not, because the data scientist has no experience with this particular process before. So being unbiased is a good thing because you're open to all sorts of possibilities, but being biased is also a very good thing in this context because you have certain gut feelings, certain inherent understandings where you can say it ought to be like this. Dear data scientist, can you check out whether it really is like that? And using that way of thinking, you generally arrive at the solution a lot sooner than if you simply analyzed everything from scratch. Again, I've seen many projects where if the data scientists are left alone, they come up with all sorts of interesting conclusions that they happily present to a room full of domain people and say, hey, look what, we've discovered this and that. But to everybody in the audience, these are things that are known a long time ago and they are not exciting at all. So again, we need that conversation to be able to place things into proper context and to see whether discoveries that are being made in the data are genuinely new and interesting and relevant to the particular problem at hand. Which leads me again to conclude here, these two roles, they need to communicate with each other on a regular basis, and so they need to be able to establish a common language where they can exchange ideas. I've attempted to plot here some practical pieces of technology that exist, particularly in the oil and gas industry, that require a certain amount of domain knowledge and a certain amount of data science expertise. So across the horizontal axis, I've gathered domain knowledge from simply being aware of a situation, having some foundational education in that sphere, having practical skill through experience, and being advanced enough to be able to teach that skill and knowledge to others. And on the vertical axis, we have data science, beginning with the most basic stage where we simply have data, numbers. Then we upgrade to information, where we know which time series correlate with what, to have some sort of clustering idea of our data. We progress to knowledge, where we have static models. Static models are not time dependent. Understanding is where we have time-dependent models. We know causes from effects. We know how long it takes from cause to effect. And ultimately, we get to what you might call wisdom, which is where you have dynamic models with pattern recognition, that you know what's going to happen, and through the pattern recognition, you also know what it is, right? And in that framework of domain knowledge and data science expertise, you can now plot various technologies that we might have. So for instance, one of the most popular pieces of AI technology is predictive analytics, making a forecast. So I say that requires the skill level of domain knowledge, in other words, education and experience, to be able to properly communicate knowledge to that system. On the other hand, it requires dynamic models, time-dependent models, to be able to actionalize. But predictive analytics just give you a forecast, right? Tomorrow at noon, something is going to happen. What you really want to know is also what it is that's going to happen. For that, you need to slot one slot up, both in domain knowledge and wisdom. You need pattern recognition, and you need advanced domain knowledge, in the sense that you need somebody capable of really injecting that knowledge to the system. So that's the point I'm trying to make, is that you need very knowledgeable people on both fronts to have this talk with each other and make things happen. And so as we progress along these 5 stages of data science capability, we need to have that data science capability in the form of a data scientist who is sufficiently knowledgeable and experienced to make that happen. But we need to inject into it domain knowledge so that we can proceed from the stage of knowledge where we have connectivity between various elements of data. But now we need the insight of a domain expert to say, this aspect and that aspect, they're really important, and they are connected in a meaningful, causal, physical, worldly way, so that we can put them together. And this is a result necessarily of that conversation. So I want to conclude here by saying that domain expertise in general is absolutely essential. One individual cannot have all the required skills and knowledge to do that. Particularly one individual who is relatively young, particularly not. I've seen in multiple examples where oil companies get a summer intern from a university, having studied perhaps 1 or 2 years at university and is an undergraduate student. And that individual, in the 3 months that they have for their internship, are meant to figure out a complex artificial intelligence application. It's a responsibility that is far too great for a person like that to bear. The outcome might be a fairly interesting bachelor thesis for that university degree, but it is not going to yield a useful, actionable software utility that can really be used in the field. So that may be something that you do to get an interesting insight, to keep somebody busy, to kind of dip your toes into the data science water. But you cannot realistically expect a project like that to actually succeed. You require people who are sufficiently knowledgeable and experienced in both realms to work together to make it happen. Generally, both of these roles require multiple people. In the oil and gas industry, you generally don't have one person who knows everything. You might need an expert for a particular kind of equipment, like an expert for the pump, an expert for the compressor, an expert for the turbine. You might need an expert on the actual oil and gas substances themselves. You might need an expert for the process control system, an expert for the data archive or historian system. So we're already talking about a group of maybe 5 or 6 individuals from the oil and gas side. From the data scientist side, we might need 1 or 2 actual data scientists. You might need an artificial intelligence engineer who is responsible for operationalizing the data science in an artificial intelligence piece of software. You might need a software developer or 2 to, for example, write a software interface or a user interface or a graphical display. And so again, from the data scientist side, you're also easily talking about 5 or 6 individuals. So in totality, we might be talking about a team of 10 people plus that are involved in a project like this. I'm talking mainly about the roles of data scientist and domain expert, but I'm not necessarily talking about just 2 people. Beyond that, beyond those 2 roles and them working together, you need even more to make the project be successful. Namely, you require, of course, project management. And management needs to support this project mainly through supplying time enough to do it and budget enough to, of course, pay for all the people and the equipment and the data and to allow this to go forward. Lastly, you need the support of the users. The users are the people who are going to utilize whatever model or software is being developed here after it has been fully developed, right? Once we agree that all of this really is accurate and actually works and is actionable, some people are going to have to take that actionable result and act on it. So for predictive maintenance, for example, that's your maintenance crew. Again, the maintenance crew is of course not one person, could be hundreds of people. And so this group of end users is going to have to learn how to use that tool, get comfortable with it, and that is a process known as change management, where these people also have to discover psychologically that this is helping them, that it is in their own interest to use that kind of tool, as opposed to thinking of the tool like it will make their jobs redundant and they may be fired soon. I've seen, again, many cases in which the end user group thought of the artificial intelligence tool as the enemy because it would essentially get them fired. And there was a boycott of the system, which was effectively not used. So it requires this kind of communication with the end users, with management, with the data scientists, with the domain experts to make all of this work, both technically as well as organizationally, so that you end up with a tool that actually gets deployed in the real world. So ultimately, data science is a team sport in which we have to work together as a team, supporting each other to finally make it all work. Thank you very much for your attention, and I look forward to answering your questions.